All right, so what I want to talk about here is the concept of a shear force and bending moment diagram. I just want to introduce it so you guys have the opportunity to see how one of these things gets built, as well as to um, see how it can be used in a real life example, right? So if we were to start, let's begin with a structure. We're going to look at a simply supported beam, and what that means is that the beam is supported by pin joints on either side, right? And pin joints on either side imply that the ends of the structure cannot support moment. Right? So if we're thinking about why, if one thing that I'll challenge you guys to go out and do is take a look at the support structures on the ends of bridges, right? And you'll notice that there are these large steel dowels that the bridge is supported by. The purpose of that is to act as a pin joint, meaning that we won't generate moment on the ends. Now, the example that I want to draw here, right, we have this beam, and that beam is a length L. And the scenario that I am going to describe here is, let's say that we have some construction going on and we want to take and drive an excavator out on the bridge. This is our bridge here, simply supported span. That excavator has weight W, and as it's driving out along the length of the bridge, right, it is moving to some point, which is a distance away from the end here that we'll call D. What I want to look at is, at what point does the bending moment in this structure reach a maximum? Or for what value of D do we generate the largest bending moment in this structure? So intuitively, we can think that if we were on the construction team that was working on this bridge, right, and we wanted to figure out when or at what point would the excavator be producing the most stress in the structure, we would think intuitively that that would happen when the weight is in the middle, or when the excavator reaches the middle of the span. We can understand that intuitively, and let's call that more or less our gut check, right? So we think that it would make sense that when we go through the math and solve this problem, that the math should also tell us that when the weight is in the middle, it is going to produce the most significant stress in the structure. So the first thing I'm going to do, which is the first thing that we'll always do with these problems, is to construct a free body diagram. So I will redraw the structure here, right? And we're going to have some force on the left and some force on the right. Let's call this one F1. Let's call this one F2. And let's call this point O, because we will ultimately need to take the sum of the moments. I'm going to draw now a dotted line here. Now, you can kind of see as I'm constructing this analysis, I've taken and I'm just sort of starting with the picture of the beam, and right below that, I'm doing the free body diagram. You'll see right below that, I'm going to construct the shear force diagram, and then below that, I'm going to construct the bending moment diagram. So we'll add W to this drawing here, right? And we can take and first do, I'm going to use the margin over here. We'll first do the sum of the forces. I'm going to create a coordinate system. Right, so let's call this X and call this Y. And I want to take now the sum of the forces in the Y direction. right? So we have two reaction forces acting the positive y direction, right? So positive y meaning that these forces are pointing in the direction that we've pointed y in. And so we get F1 plus F2. And now W is pointed downward or opposite the direction of our coordinate system. And that's going to be negative W. And this has to be equal to 0. Now, we have two unknowns in this system, right? We don't know what F1 is and we don't know what F2 is. So, from an algebra standpoint, we know that we need to have two equations in order to solve for these two unknowns. So the second equation that we're going to write here from the statics case is to take and calculate the sum of the moments about point O. So point O here. Now, why do I choose point O, right? I could choose point O for the sake of reducing the complexity of the problem. In order to remove the one of our unknowns, I can choose a point to calculate the moment about which the force goes through. So O in this case can occur directly above F1 or that reaction pin. The same thing could occur on F2, right? Where if I were to pick this location, I would cancel out F2 in the sum of the moments. But let's call the counterclockwise direction here positive. So moments that produce a positive rotation are going to generate positive moments. So in this case, take point O, take W, right? W tends to produce counterclockwise rotation. You can see that. And we know that W occurs at a distance D. So the moment produced by W is W times D. That's in the positive direction. And then in the negative direction, going in the opposite way here, negative F2 times L, right? The moment that is produced by F2 around point O has a moment arm of L, right, from above. This also has to be equal to 0, right? So from statics, in order for this system to be in static equilibrium, not moving, right, the sum of the forces and the sum of the moments have to be equal to 0. So now we have two equations and two unknowns, so we can solve for F1 and F2 using these two equations, right? So let's go ahead and we can label these. Let's say that this is equation 1 and this is equation 2. And if we take equation 2 and we move some things around here, right? So I can take F2 times L and move it over to the other side because it's subtracted. And then I can divide both sides by L. So that's what I'm going to do to find F2. F2 is equal to W times D over L. I can now take this result, F2 is equal to WD over L, and plug that into equation 1 and solve for F1. So we have F1 plus WD over L minus W is equal to 0. We can move everything over to the other side, so we can get F1 is equal to W, adding this to the other side, minus WD over L. And we can pull the W out and get W times 1 minus D over L. So we've solved for both of our reaction forces here. And we find that F1 is equal to W reduced by some magnitude based on the distance D. And similarly, we get the same thing for F2. Now, if I'm going to begin to construct the shear force bending moment diagrams, and we'll start with the shear force. And I'll draw some axes. So again, this is our x distance. And we'll go into detail in the lecture what the rules are for constructing this, but I just want to give you a flavor for how this is done. The first thing we'll do is start on the end, right? The end of this structure is going to, we'll actually start because it's a free end. The shear force at the free end is going to be 0. We're going to increase up to the magnitude of F2. We're going to jump up, and the magnitude of F2 is this WD over L. That will remain constant. The shear force in the section of this will remain constant until we hit our next magnitude, our next application of load. So the magnitude here, again, this is shear force as a function of x. The magnitude here is going to be WD over L. And we're going to go up to the point of the weight. We will actually jump down the magnitude of the weight. So the change in shear force at this location is going to be W. And this will then bring us to the application of our last load, which again is going upward, brings us back down to 0. That helps us with meeting our boundary conditions. And the magnitude here is going to be equal to F1, right? Negative F1 in this case. So this is W times 1 minus D over L. And we can do the same thing with our bending moment diagram. Now, the relationship between moment and shear force is they are related to each other. You can think about it either as an integral or a derivative, right? Which, what I mean when I say that is that the integral of the moment here, right, is going to be equal to the shear force, or the derivative of the shear force is going to be equal to the moment. So if we take and draw this, if the shear force is equal to the the derivative of the moment, then the slope of the line along this length has to be equal to the magnitude of the shear force in that section. So the shear force is constant along the length of here, which says that this moment is going to increase with a linear slope that is equal to the shear force. The slope of this line is the shear force. So we can say that that's WD over L. On the opposite side, this is negative, has a negative slope, which is going to be equal to W times 1 minus D over L. Right? And we can see that the maximum magnitude of moment occurs at the location of the applied loading, right? If we call this M max. So this distance here is L minus D, and we could take and use now the shear force and calculate what the maximum magnitude of moment is. So the maximum moment, right, is equal to WD over L times L minus D. This is the maximum magnitude of moment which occurs at the point of application of load. Now, what we want to accomplish is to determine for what value of D. So as the excavator is driving out along the length of the bridge, what magnitude of D is going to result in the maximum moment, right? At that point, that is when we expect that the structure is most likely to fail. And we can use a really simple concept. It at first might seem a bit advanced, but it actually proves to be very useful. We can use a simple concept from Calculus 1, right? Very simple concept in calculus, which is how do we maximize a function? And the function that we want to maximize today is this maximum moment. And we've already defined this maximum moment as a function of d being the distance. We can take that and rewrite it as the weight times d. Let me see, I sort of times d divided by L, this multiplied by L minus d. Again, this comes from the magnitude of our reaction load, right? So this is F2, and this is the moment arm. Of F2, and this is telling us what the magnitude of our maximum moment is. So what I'm going to do is actually pull this d divided by L into this quantity here. So what that's going to look like here is we're going to have W times d minus d squared over L. So again, I take and I multiply this by d, I divide that by L, the L's cancel out, and then I have d squared over L. We can see that quantity. Now, here's the part from calculus that is important and useful. We want to maximize this function. So if we want to maximize this function with respect to d, right, the approach that we can use to do that is to first calculate the derivative of this maximum moment, right, with respect to d. So m max, right, we're going to calculate the derivative of that with respect to this quantity d, and then we'll set that equal to 0. This will maximize the function. So if we calculate that derivative, and you may have to go back and refresh yourself on calculating the derivative of a polynomial. This is a polynomial here, right? We're going to get w times the derivative of d with respect to d is 1. And the derivative of d squared with respect to d is going to be 2 times d over L here. And we want this quantity to be equal to 0. This is going to give us the maximum value of maximum moment for the independent parameter d. Since this is w, we want to solve this now for d. This is w times this quantity. We can actually get rid of w, right? So if we divide both sides by w, we still get 0 on the right-hand side. And we get 1 minus d2d over L is equal to 0. We can pull this over to the other side and rearrange a bit. I'm going to just rewrite that to be 2d over L is equal to 1. I multiply this over to the other side. I get 2d is equal to L. And then finally, d equal to L over 2, which is the result that we were looking for. So this passes the gut check, right? So we said to ourselves, where do we think that the result is going to be the worst case for the bridge? This is when the excavator is at the middle of the span. We went through the process of developing shear force and bending moment diagrams. Now, I don't want you guys to get too worried about too worried about this in this context. I'm going to give you a full set of tools for developing these. We're going to go a bit more into detail surrounding how I constructed the shear force and bending moment diagrams in this video. I'll show them again here. But ultimately, it gives us the result that we expected, and we did so with a formulaic approach that is ultimately the approach that engineers use when they're designing these structures. So when we start with an example like this, you can see intuitively how that works. As time goes on and you start working with and thinking about more complicated structures and more complicated arrangements of load, going back to these fundamental examples will really help inform your intuition and make you a better engineer. Thanks for watching.